You know, every single time you click a link, tap a button, or type a web address, something amazing happens. A secret conversation, a high-speed dialogue flashes across the entire globe in just milliseconds. It's what makes the entire internet work. And today, we're going to decode.
Think about it. It's an action you probably do hundreds of times a day without a second thought. You see something interesting, you click it, and boom. Just like magic, the web page is right there on your screen.
But what is that magic really? What happens in that split second between your click and the page loading? It's not instant, and trust me, it's not simple. What's actually happening is a really fast conversation between two main players. First, there's your browser. Let's call it the client. And it's talking to a powerful computer somewhere else in the world, which we call the server. They're using a very specific language to get you what you ask for. And in this explainer, that's exactly what we're going to do. We're pulling back the curtain on that secret language. By the end of this, you'll understand exactly how the web talks to itself. So let's start with the language itself. It's called HTTP. That stands for Hypertext Transfer Protocol. At its heart, HTTP is just the rulebook for this conversation. Your browser, the client, sends out a request for something. You know, an image, a video, the main code for a web page. And the server's job is to send that thing right back. All of this happens over something called TCP, which is kind of like the internet's reliable delivery service. It makes sure the messages actually get where they're going. Now, here's a really important, kind of weird concept. HTTP is stateless. What that means is the server has total amnesia. Every single time your browser talks to it, it's like they've never met before. The server has zero memory of any past conversation. Now, that sounds like a huge problem, right? Well, stick with me, because the web has a very clever way of getting around it. All right, so these HTTP conversations can happen in two main ways. You can think of it as either a whole bunch of really short, separate chats, or one long, much more efficient conversation.
So on the one hand, we have the old way, non-persistent HTTP. This is like making a phone call, asking for one thing, hanging up, and then dialing the exact same number all over again to ask for the next thing. It's super inefficient. On the other hand, we have the modern way, persistent HTTP. Here, you make one phone call and you just keep the line open to ask for everything you need. Way faster.
And let's just see how inefficient that old way really was. To get a web page with just 10 images, your browser would have to open a connection, request the main file, then close it. Then open a brand new connection for the first image, get it, close it. Then another one for the second image, and on, 10 more times. The amount of extra work is just huge.
The key takeaway here is this. Every single object costs 2 round-trip times, or RTTs. An RTT is just the time it takes a signal to go from you to the server and come all the way back. So you're paying 1 RTT just to set up the call, and another one to actually ask for the file and get it. When a web page has hundreds of little objects, those RTTs add up, and they add up fast. That's what made old websites feel so slow.
Okay, so we know the structure of the conversation, but what are they actually saying? Let's take a look at the messages themselves. This is what a real request from your browser looks like. And the coolest part about it is that it's simple. It's just plain text. You can literally read it. It's saying, get me this file, I'm looking on this host, and check out that last line. Connection, keep alive. That right there is the instruction to use a modern, persistent connection. It's telling the server, hey, don't hang up the phone. And here's the server's reply. The most important part is right there on that first line, 200 OK. That's the server saying, you got it, success, here's the file you wanted. Then it just gives a few details like what kind of file it is and how big it is, and then there's the actual content of the file itself. Now, 200 OK is the one you always want to see, but there are others you've probably run into. A 301 just means, hey, that page is moved, here's the new address. The famous 404 means the server looked, but it just couldn't find the file you asked for. And a 505, that's basically the server saying, sorry, I don't speak the version of the language you're using. Okay, so let's go back to that amnesia problem. If HTTP is stateless, how does a website possibly remember what's in your shopping cart, or how does it keep you logged in between pages? The answer is a really clever workaround called cookies.
So here's how this little dance works. The very first time you visit a site, the server sends back a little message that says, set cookie, and it hands your browser a unique ID number, like a digital name tag. Your browser saves that tag. Then, from that moment on, every single time you talk to that server, your browser shows it the name tag. The server then uses that ID to look you up in its own database and go, oh, right, I remember you. You're the one who had those shoes in your cart.
And this is why it all matters. Cookies are the foundation for basically the entire modern web experience. They're what keep you logged into your email, they're what remember the items in your Amazon cart, and they're what let Netflix give you personalized recommendations. They create a stateful experience on top of a protocol that has no memory. It's pretty genius. All right, now that we understand the conversation, let's look at two final pieces of the puzzle that make it all happen ridiculously fast, something called caching and a major upgrade called HTTP/2. You can think of a web cache like a local library branch. Instead of everyone in town having to drive all the way to the one main library downtown to get a popular book, the local branch just keeps a few copies on hand. A cache does the exact same thing for web content. It's a nearby server that stores popular files closer to you, so you don't have to go all the way across the world to the main server every time. And the effect of this is absolutely dramatic. This chart shows the traffic on a company's main internet connection. Before they used a cache, it was running at 97% capacity. I mean, it was totally maxed out, a huge bottleneck. After installing a cache, that usage dropped all the way to a much healthier 58%, because the cache was handling a huge chunk of the requests all by itself. And what did that actually feel like for the users? Well, the average time it took to load a page just plummeted. It went from several minutes all the way down to just 1.2 seconds. That is the power of putting content closer to the people who want it. And finally, there's HTTP/2, which fixes a nasty problem called head-of-line blocking. Okay, imagine you're at the grocery store. You've got one tiny item, but you're stuck in line behind someone with a massive, overflowing cart. That was the problem with the older HTTP/1.1. Small files had to just sit and wait for huge files to download first. HTTP/2 is like opening up a dozen new checkout lanes at once. It breaks that big file into tiny little pieces, or frames, and it sends the smaller files in between those pieces. Everything gets processed together, and the whole experience is just so much quicker. So we've gone from these slow, clunky, one-off conversations to this single, super fast connection where all the data is beautifully mixed together for maximum speed. But this leads to a fascinating final question. If all of this data is now flying through one single pipe, what happens if just one tiny piece of data gets lost along the way? Does it still create a massive traffic jam for everything else? Well, that's a story for HTTP/3.